There's a few noteworthy facts that come out of that theorem we just proved. One of these being this corollary. So let's say n is some fixed integer greater than or equal to 2. A is congruent to 0 mod n is exactly the same thing as n divides a. Remember, these are statements, these are not calculations. These are statements that are either true or false. So for example, if I say 3 divides 15, well, we know by definition that means 15 is equal to 3 times some integer q. Other way to think about it, let's notice n here is 3 and a is 15. So let's apply that structure to this. So 3 divides 15, this corollary is saying that that's the same as saying 15 is congruent to 0 mod 3. And think about what that means. What does it mean to say 15 is congruent to 0 mod 3? It's saying 3 divides 15 minus 0. But that's exactly the same as, this here is exactly the same as saying 3 divides 15. This is not a proof, it's just an example to illustrate what this corollary is saying. It's equivalence of definitions. Okay, the thing to keep in mind that this theorem tells us also is you're always going to end up with a number from 0 to n minus 1 when you're doing mod n. This is something that I've actually said before, but I didn't say it in the context of modular arithmetic specifically. Here's a little side note to remind you. The final answer in modular arithmetic is always between 0 and n minus 1 inclusive. We call these residues modulo n. And we talk about reducing numbers mod n. So back to the example from earlier, if I say reduce 27 modulo 12, I'm basically saying kick 27 down by multiples of 12 until you get something that's between 0 and 11. The very informal way to do this is to keep subtracting 12 until you get the smallest positive integer you can. And so, well, what does that end up being? It ends up being 3. This is a beginner's way of doing this. The more advanced way is to apply the division algorithm to 27 and 12. And what you get is your remainder will always be between 0 and 11 inclusive. And so 27 is congruent to 3 mod 12. So here's another fact. Again, we're going to let n be a fixed integer greater than or equal to 2 if a is congruent to b mod n and c is congruent to d mod n. Then we can treat these congruences in a way as if they were equations. We can add a plus b and we can add b plus d, and we're going to get the same congruence result. They're both congruent to each other mod n. Same thing if we do multiplication. AC will be congruent to BD mod n. The proof for this is straightforward and uses the definitions. So what I'm going to do is I'm just going to ask you to pause the video, read this proof. If there's any parts of it that seem unclear, I want you to go back and review the definitions that we discussed at the beginning of this section. And then, you can always ask questions if you still have them. Okay, let's look at an example. Oops. So there's that word reduce that I was talking about. We want to reduce 2,370 modulo 11. So I could repeatedly subtract 11 from 2370 to get something that's between 0 and 10. Or I could try to do a lot of subtractions at once in a way. One helpful thing when you're doing modular arithmetic is to keep multiples of the number you have in mind. So what would be a helpful multiple of 11 that will help us bring down this number? Well, the idea they suggest is negative 2200. Negative 2200 is a multiple of 11, which means it's congruent to 0 mod 11. We can add this congruence to this congruence. And what will we get? We get that 2370 is congruent to 170 mod 11. We're still not done. We haven't brought 170 down to a number that's between 0 and 10, but we can keep doing that. Find another convenient multiple of 11 to bring 170 down. 110, or I should say negative 110, is a convenient multiple of 11 that will bring this down significantly. So if we subtract 110 from 170, we get 60. So now 60, okay, we're getting closer to being something between 0 and 10. What's another convenient multiple of 11? Well, 55. So if we take away 55 from 60, we get 5. All this amounts to saying that 2370 is congruent to 5 mod 11. You wouldn't necessarily write these. You would probably do these in your head if you're going to take this approach to reduce something modulo n. So to practice with this, go ahead and give this hands-on exercise a try. Your goal is to reduce 12,457 to the smallest non-negative residue modulo 11. Remember, this is another way of saying basically the remainder when you divide by 17, but rather than applying the division algorithm, we want to try to kick this down by taking away multiples of 17 as needed.